let's go over practice test 2 here. Okay, so number 1. What value of C, this thing here, makes the table below a probability distribution? Well, there are only 2 things you need, right? You need all of the numbers to be non-negative, that is, none of them can be negative, and you need all the numbers to add up to 1, all the probabilities to add up to 1. So if I add up all the ones I have and then subtract from 1, I'll find out what C has to be, right? I could write it down. C has to be 1 minus 0.15 plus 0.1 plus 0.04 plus 0.13. Right? So what is that? 0.25, 0.29, 0.42. So C has to be 1 minus 0.42. So C is 0.58. Okay, number 2. A bag contains several lipsticks which are indistinguishable except for color. There are 3 lipsticks of the ballerina shoes color, 2 of the blushing berry color, 1 Brazil nut, and 3 I pink you're cute. And yeah, these are real lipstick colors. If a lipstick is drawn at random from the bag, what is the probability that it is named after a fruit or a nut? So let's see. There are 3, plus 2 is 5, plus 1 is 6, plus, so there are 9 altogether. 9 lipsticks. And how many of them are named after fruits or nuts? 2 blushing berries and 1 Brazil nut, so 3. Right? So the probability named for a fruit or nut is 3 out of 9, or 1/3. Okay, a single card is drawn from a standard deck and a single die is rolled once. Let E be the event that the card is an ace, F the event that the card is a heart, and G the event that the die shows a number less than 3, so 1 or 2. List all the pairs of events that are mutually exclusive. And so when I need to do that, I usually just write them all down, EF, EG, FG, and then I consider the pairs one by one. So E and F, are those mutually exclusive? E is the card is an ace, F is the card is a heart. Are those mutually exclusive? They're not mutually exclusive if there is even one outcome that would make them both occur, right? That is in both events. So here, the King of Hearts, you could draw the King of Hearts, and then E would happen. You could draw the Ace of Hearts, and then E would happen, the card would be an ace, and F would happen, the card would be a heart. So those are not mutually exclusive. How about E and G? Is there any outcome that could make both E and G happen? That would be the card is an ace, and the die shows a number less than 3. Sure, right? An ace, the ace of spades, and a 1. So those are not mutually exclusive. Let's see, F and G, card is a heart, and the die shows a number less than 3. That could easily happen. So those aren't mutually exclusive either. Right? So the answer here is there are none. No pairs that are mutually exclusive. Okay, what about these probabilities? What's the probability of E? The probability the card is an ace. For that, it doesn't matter what happens on the die. Right? Really, it only matters whether the card is an ace. And there are 4 aces out of 52 cards, so the probability is 4 out of 52, or 1/13. For F, the probability that the card is a heart, there are 13 hearts out of 52 cards, so it's 13 out of 52, which is 1/4. And G is the event that the die shows a number less than 3, so that's a 1 or a 2. So there are 2 outcomes in G and 6 outcomes possible for the die, so this is going to be 2 out of 6, or 1/3. Finally, what's the probability that both E and G occur? That would be probability of E and the probability of G, so probability of E and G. Well, the easiest, we can compute this most easily when E and G are independent. So let's think about that. E is the card is an ace, and G is the die shows a number less than 3. Well, those are going to be independent, because what happens on the card doesn't affect the probability of anything particular happening on the die, and vice versa. So those are independent. So the probability of E and G happening is just the product of the probability of E and the probability of G, which is 1/13 times 1/3, or 1/39. Okay, the last one of these on this page. 2 dice are rolled, 1 red and 1 green. Let E, B get a 2 on the red, F is get an even number on the red, G is get a sum of 5, H is get a sum of 2. List all the pairs of mutually exclusive events. So once again, I'm just going to list all the pairs and then cross out the ones that aren't mutually exclusive. E and F, E and G, E and H, F and G, F and H, G and H. That's all the pairs. Right? There's no reason to list, say, FE, because that's the same pair as EF. Okay, E and F, are those mutually exclusive? Get a 2 on the red and get an even number on the red. No, right? A 2 is an even number, so if you roll any even number on the red, if you roll a 2 on the red, then both E and F have occurred. So those are not mutually exclusive. E and G, a 2 on the red and a sum of 5. If you got a 2 on the red and a 3 on the green, that would be an outcome that would make both of these events occur. So they are not mutually exclusive. How about E and H? A 2 on the red and a sum of 2. Those are mutually exclusive, because if you get a 2 on the red, you'd have to get a 0 on the green, right? And that's not possible. So those two can't happen at the same time. They are mutually exclusive. What about F and G? An even number on the red, so a 2, 4, or 6, and a sum of 5. Sure, you could get a 2 on the red and a 3 on the green, or a 4 on the red and a 1 on the green. That would make both of those happen, so they are not mutually exclusive. What about F and H? Even number on the red and a sum of 2? Nope. Any even number on the red. The only way you can get H, the only way that can happen, is if you get 1 on each of the dice. And so that's not going to give you an even number. Those are mutually exclusive. What about G and H? Sum of 5 and a sum of 2, can't have both, so those are mutually exclusive. All right, let's do this one. Number 5, suppose X is normally distributed with mean 127 and standard deviation 14. Of course, you have to know how to read the notation. Trying to focus here. Then, well, mean, standard deviation, so mu is 127 and sigma is 14. Let's see, make a rough sketch of the curve. Don't put in any y values, but label mu and mu plus or minus sigma on the x-axis. All right, so we don't know what the curve's really going to look like, but it's close enough. Right? Here's the means right underneath the highest point, so that's mu, which is 127. And then mu minus sigma would be 113. That would happen right about here where the inflection point is, 113. Mu plus sigma, that would be out here, and it would be 127 plus 14, or 141. Okay, what's the total area under the curve? The total area under any PDF is 1. Has to be. What's the area to the left of 112? Right, so X has this distribution. I'm going to write this out. Probability X is less than 112, or less than or equal to, it's the same thing. So this is going to be a normal CDF of minus infinity, but of course we'll use the TI's version of that, minus 1 E99 to 112, with mean 127 and standard deviation 14. And let's see if I can get this up here. We need normal CDF of minus 1 EE99, comma, 112, comma, 127, comma, 14. It's about 0.142. Close enough? So this is about 0.142. What's the probability X is greater than 120? Well, it's the same kind of thing, right? It's just a normal CDF of 120 to infinity, but the TI's version of that. And then the mean, and then the standard deviation. So, normal CDF of 120, comma, 1 EE99, comma, 127, comma, 14, Looks like about 0.691, close enough. What's the number d such that the probability that x is less than d is 0.41? Right? Probability x is less than d, that's the area to the left of d. So we're looking for the d on the x-axis here, so that the area to the left of d is 0.41. If d were here, the area to the left of it would be 0.5. So I'm going to put d in right about there, just, in the picture. Well, how do I find d then, if I know the area to the left of it? This is going to be inv norm of 0.41, 127, 14, and let's just do it. Inv norm of 0.41, 127, 14. Looks like about 123.81. How about that? And this one, probability x is between 103 and 137. Well, I don't think I need to write it out. We'll just do it here. That'll be a normal CDF, right? 103, 137, and now the mean and standard deviation, 127, 14. It's about 0.719. Okay, here's another one. The speeds of cars past a certain point on Interstate 81 have been found to be normally distributed, with mean 62 miles an hour and standard deviation 12 miles an hour. If a car is selected at random from those passing the point, what is the probability that it is going faster than 65 miles per hour? So we're just going to let x be the speeds of the cars, right? And we want to know what's the probability that x is greater than 65. Right? So this is, x is normally distributed, we've been told that, with mean 62 and standard deviation 12. So this is just going to be another normal CDF. Right? Greater than 65, so 65 is going to be the left-hand point here. 65 to infinity, but as usual, we'll use that. And then mean, which is 62, and standard deviation, which is 12. And we'll just put this in. Normal CDF of, what is it, 65 to plus infinity, so 1. Can we see this? Yeah, okay. Comma, and then the mean is 62, and the standard deviation was 12. About 0.401, how about that? That's close enough for us. Okay. If x is normally distributed with mean 0.3 and standard deviation 0.014, what's the z-score of the x value 0.29? Well, this is just the z-score formula, nothing magic in here. You just have to be able to read this, but you have to be able to do that to do most of these problems. Z-score formula is z is x minus mu over sigma. So in this case, that is 0.29 minus 0.3 over 0.014. And that turns out to be, let's see, should we just do it? 0.29 minus 0.3, that's a pretty easy one to do in your head. And then divided by 0.014, looks like around, 0.714, negative 0.714 minus 0.714. Okay, onward. All curves shown below are normally distributed with mean 10 and standard deviation 1. Sketch the region corresponding to the indicated probability. So let's see, the probability x is less than 8, so that would just be the area to the left of 8 under the curve. That. The probability x is greater than 9, well, okay, that's all the area to the right of 9. The probability x is between 11 and 12. It's just that little area in there. This one might be a little more confusing. probability x is less than 8 plus the probability x is greater than 11. Well, the probability x is less than 8, that's this little area back here. The probability x is greater than 11, that's this area. And so that's what's meant here. If you add this area and this area, in other words, add the shaded areas, you would get this amount right here. Okay, suppose that a population is normally distributed with mean 5 and standard deviation 0.9. What's the first quartile? Right? The first quartile is just inv norm of 0.25, because the first quartile is the 25th percentile, right? And then the mean, and then the standard deviation. So this is inv norm 0.25, comma 5, comma, oops, I've forgotten, 0.9. About 4.39. Okay, number 10. Scores on a certain test are normally distributed with mean 1,000 and standard deviation 100. What is the lowest score a student can get and still be in the top 10%? The cutoff for the top 10%, right, here's a little picture. I draw pictures a lot. The cutoff for the top 10%, right, you want to know the cutoff for this area right here. Well, that cutoff is also the cutoff for the bottom 90%. Right? If this is 0.1, then this area has to be 0.9. So this is the 90th percentile, P90. So the cutoff score is P90, which is just inv norm of 0.9, and then the mean, and then the standard deviation. Oops, 100. And here we go. Inv norm of 0.9, comma, 1,000, comma, 100. 1128.15. 1128.15. Scores are probably actually integers or something, so we would have to round, but that's good enough for this. They didn't say so. What is the highest score a student can get and still be in the bottom half? Well, here's a picture. This one I don't even need to do a calculation for. The bottom half, in the normal distribution, right, the mean and the median are both right at the same point. And so this area is 0.5. And so the highest score a student can get and still be in the bottom half is the mean, right, which is 1,000. All right, number 11. Judd has 1,052 values from an experiment on fruit flies. What is the best way for him to determine whether the values are probably from a normally distributed population? The best way to determine whether data is from a normally distributed population is a QQ plot, or a normal probability plot. We don't need to make them in this class, but you need to know their names, and you need to know both names for it because a multiple choice question could have either one. All right. Suppose that x is normally distributed with mean 100 and standard deviation 10. Which of the following is the probability statement equivalent to what is the area under the curve between 80 and 120? This is easy. This is 100's the mean. It says so right there. And so this is 80 over here somewhere. This is 120, right? The area under the curve between 80 and 120 is this, right? And so we would be looking for the probability that x, we're told x, random variable x has this distribution. We're looking for the probability that x is between these two, 80 less than x less than 120. And that's C right here. Okay, number 13. The body lengths of common house sparrows are approximately normally distributed with mean 6.3 inches and standard deviation 0.25 inches. The Common House Sparrow database has information on 375,412 sparrows. About how many of these birds can be expected to have body lengths between 6 and 7 inches? Well, if we find, we know these are normally distributed, and we know the mean, and we know the standard deviation. And so we can find the probability that if you picked one of these things at random, its body length would be between 6 and 7 inches. And we can interpret that probability as a percentage of the population really it's a very large sample, that is between 6 and 7 inches. Right? So then we'll know the percentage that have values between 6 and 7 inches, and we can compute the actual number, because that's what's asked for, how many. Right? So first, the probability, first, we're going to let x be the length of a randomly chosen sparrow, of the sparrows. Right? So we're looking for the probability that x is between 6 and 7. And that's just a normal CDF. It'll be approximate, I'm sure. So let's see, I want normal CDF of 6, 7, I've forgotten these already, 6.3 for the mean, and then 0.25. So that's about 0.8824, let's say. 0.8824. So about 88.24%. About 88.24% have body lengths between 6 and 7 inches. But the problem asks how many of these birds can be expected to have body lengths in this range. So that is 88.24% of this number right here. So we're just going to do this, 0.8824. Can you see this? Nope, I can't. 0.8824 times whatever that is there, 375,412. 331,264. Sorry. 0.8824 times 375,412, which was, what again? 331,264. Have body lengths in the right range. Right? Okay. Number 14. In how many ways can the 40 members of a 4-H club select a president, a secretary, a president, a vice president, a secretary, and a treasurer, assuming that no one can hold more than one office at a time? The simplest way to do this is just by the fundamental counting principle, right? You can think of picking a president, a vice president, a secretary, and a treasurer. When you go to pick the president, you have 40 choices because presumably anybody can be president. But the person who is chosen for president can't also be chosen for vice president because no one can hold more than one office at a time. So you only have 39 choices when you go to choose a vice president, and then 38 for secretary, and then 37. Right? And then you just multiply those together, and I guess I could do that. 40. Uh, 2193360. 2193360. That is certainly the easiest way to do it. You could also think of it this way. You're going to be picking 4 people, and order matters, because think of like putting signs on the wall with a P, and then a VP, and then an S, and a T. And you're going to pick 4 people, and you're going to stand them up underneath these signs, and whoever's standing under the P sign is going to be president, and so on. So if you choose them in the order Alice, Bob, Carol, David, then Alice is president and Bob is vice president. But if you choose them in the order Bob, Carol, Alice, David, then Bob is president and Carol is vice president. And so the order in which you choose them matters. So choosing 4 people from among 40, where order matters, that could be written P of 40, 4, or 40 and then a P and then 4. And I write it that way because your calculator does. Right? Let's go ahead and do that on the calculator. So you are reminded how it is done. You put 40 on the screen, and then you go to math. Where is it? Math, and then over to probability, and then down to NPR there, the second thing. Hit enter, and then put 4 on the screen. And there it is, that 2,193,000 thing. Of course, it's the same number. Okay, number 15. Are drawing a king and a heart from a standard deck of cards mutually exclusive events? They aren't, because, just as before, there is at least one outcome that makes both those events happen. Drawing a king, drawing a heart, those are the two events. Is there any outcome that's in both? Yes, drawing the king of hearts. Right? So, no. In how many different ways can a person choose 3 movies to watch in a theater playing 11 different movies? Now, there's nothing here about order mattering. All you're doing is choosing. Right? And so the number of ways to do this, it could be written C of 11, 3, or it could be written like this, which is usually pronounced 11, choose 3, or, sorry about this, but it's the way it is. People use all 3 notations. It can be written like that, right? 11 and then C3. To calculate it, you do it very much like the permutations one. Put the 11 on the screen, and then you go to math, over to probability, down to NCR, the third entry, and then 3, and there you go, 165. All right. 17. An urn contains 12 balls, identical in every respect except color. There are 3 red balls, 7 green balls, and 2 blue balls. Let me see, that's 12 altogether. You draw 2 balls from the urn, but replace the first ball before drawing the second. Find the probability that the second ball is green if the first ball is red. Okay, so you draw a ball, and you write down its color, and we're told it's red. And then you put the ball back in, and then you draw a second ball, and ask what's the probability that second ball is green. Well, because you put the first ball back in, when you go to draw the second ball, there are 12 balls in the urn altogether, of which 7 are green. So the probability here is just going to be 7/12. That is sampling with replacement. Now, number 18 is the same kind of thing, only without replacement. Right? The urn contains the same 12 balls with the same colors. You draw 2 from the urn, but do not replace the first before drawing the second. What's the probability the second ball is green if the first ball is red? Okay, so now you draw a ball out, and it's red. You set that aside. And then you reach in, and you draw a second ball out. When you go to draw the second ball, there are only 11 balls in the urn, of which 7 are green. So the probability you choose a green one now is 7 out of 11. Right? I did not use the formulas for conditional probability here because it's easiest not to. It's much easier to think your way through these problems. All right. Which of the following is not an accurate representation of the law of large numbers? Remember what the law of large numbers says? It says essentially that empirical probabilities get closer and closer to theoretical probabilities as the number of trials increases. So here, what do we have in the first part A here is an actual picture. Right? You have an increasing number of trials. Here you have means. I guess this is each of these would be each of these y values here would be the mean for that number of trials. So after 100 trials, if you went up to here, this would be the y. This y value would be the mean for first 100 trials and so on. This line is the theoretical mean here. And so what we have is as the number of trials increases, we see that the mean over those trials gets closer and closer to the theoretical mean. It may wander around a little, but in general it's getting closer and closer. So that's pretty much what the law of large numbers would say. What about part B here? Choice B. As the number of trials increases, the experimental probabilities get farther away from the expected theoretical probability. Well, that's surely an answer, right? That is not an accurate representation of the law of large numbers. What about part C? the probability obtained from a large number of trials should be close to the theoretical probability and will become closer and closer to the theoretical probability as more trials are performed. That's almost the statement of the law of large numbers, right? So the only possible answer here is B. Okay, number 20. Is the following scenario binomial? In a certain city, the need for money to buy drugs is stated as the reason for 75% of all thefts. What is the probability that 2 of the next 5 thefts result from the need for drug money? Okay, so first of all, what is the experiment here? I guess it is picking 5 thefts, right? I guess the police records for 5 thefts at random, and determining whether or not the motive for the theft was the need to buy drugs. So let's see. You just ask yourself the questions, right, to see whether or not a scenario is binomial. That is, whether or not the random variable that counts the number of successes, whatever those are, can be expected to have a binomial distribution. So, is there a finite number, a fixed number of trials? Yes, 5, right? There are 5 trials here. Are the trials independent? Well, as far as we can tell, they are. We're just going to pick 5 records at random. Are the only possible outcomes of each trial success and failure? Right? There are only 2 possible outcomes. And yes, either a theft was motivated by the need to buy drugs, or it wasn't. Right? So yes, is the probability of success the same for each trial? Well, presumably success here would be pick one for which the motive was the need to buy drugs. So yes, the probability of success would be 0.75 in each case. Right? So this is a binomial scenario. All right, let's do the next one. 21. The following is a binomial scenario. Oh, good. Glad I'm told that. It's hard. Those problems of determining whether something's a binomial scenario or not are generally pretty hard. So I'm always glad to be told. The director of a health club conducted a survey and found that 23% of members used only the pool for workouts. A random sample of 10 members was chosen. What is the probability that exactly 4 of the 10 members used only the pool for workouts? And so I'm going to let X be the number who used only the pool. That's what I'm talking about here, right? That's the number. So I'm defining success to be used only the pool, and letting X count the number of successes. The probability that exactly 4 of the 10 members used only the pool, that's going to be the probability that X is equal to 4. Since I'm looking for the probability that X is exactly equal to something, I'm going to be using binom PDF, right? And these all have the same kind of inputs, right? The inputs are N, P, X, where N is the number of trials, P is the probability of success on any one trial, and X is, well, the number of trials we're interested in, the number of successes we're interested in. So we have 10 trials, right? We pick 10 members. P is 0.23. I can write that. And then we want to know the probability of exactly 4 successes, and so it's going to be 4 right there. And so we take out our trusty calculator. Let's see if I turn this off. Is it easier to see the screen? No, it's harder. Sorry. Let's see. So we need binom PDF. That's on the distributions menu. So I go to the distributions menu and then arrow down until I find, binom PDF. There it is. Okay, and then I'm just going to put in the arguments 10, comma, 0.23, comma, 4. So it's about 0.1225. All right. Next one, what is the probability that fewer than 3 of the 10 members used only the pool for workouts? So this is X fewer than 3, X less than 3. So I'm going to want the probability that X is less than or equal to 2, because that's what it means to be fewer than 3 here. And so that's going to be now binom CDF, right? So this is I'm using binom CDF because this is the probability that x is at most 2. Probability of, okay, x less than or equal to 2, binom CDF, NP and x, so 10.23 and then 2. So this turns out to be, wish I could get a better light here. All right, same, going to go to distributions menu, arrow down until I get to binom CDF, and then put in the arguments 10, comma, 0.23, comma, and then 2. It's about 0.5863, something like that. All right. What is the probability that at least 4 of the 10 members used only the pool for workouts? Remember the probability of, so this is the probability that x is greater than or equal to 4. And the only way I can get that is to subtract 1 minus the probability that x is less than or equal to 3, right? The probability that x is at least 4 is 1 minus the probability that it is at most 3. So this is 1 minus binom CDF of 10, comma, 0.23, comma, 3. And that's going to be, I'm going to do this all at once, 1 minus, then I'm going to go to the distributions menu and go down to binom CDF, 1 minus binom CDF, 10, comma, 0.23, comma, 3, and 0.1794 approximately, 0.1794. Okay. Number 22. Find the probability that a randomly selected piece of data from a normal population will have a z-score less than negative 0.35. Let's draw a picture. So here is my normal population, and here is, so call that one x, and this will be z, right? So this is the standard normal over here. A z-score less than negative 0.35, let's see, that would be out here somewhere, right? Negative 0.35 on the z-axis. So I would be looking at I want to know the probability when I select something from over here, from the x-axis, the probability that its z-score is less than negative 0.35. Well, it would have to be over here. Whatever this number is, let's call it C over here. Whatever this number is that in the z-score, using the z-score formula, will map over to negative 0.35. Right? It's the numbers less than that on the x-axis that will have z-scores less than negative 0.35. So I want the probability that x is less than c here. In other words, I want this little area. But this little area, I have no way of computing this area over on the x picture because I don't know the mean or standard deviation. But over here, it has to be the same as this area, the area to the left of negative 0.35. So that probability that we want is just going to be normal CDF of minus infinity to minus 0.35 under the standard normal. Okay. So let's just do that. Normal CDF of minus, of course I have to use this version of infinity, and then minus 0.35. It's about 0.3632. Okay. That's the probability that if you chose a value from the z-axis under the z distribution at random, you'd get one less than negative 0.35. So that needs to be the probability of choosing an x value that's to the left of this number c that maps over to negative 0.35. Okay, got interrupted there. Let's do number 23. What z-score is associated with the 57th percentile of a normal distribution? Well, let's see. Let's draw a normal distribution here. We'll call this x, and I don't know its mean standard deviation, so we'll just say it's mu and sigma. In any case, the 57th percentile, right, it's defined by, it's the number on the axis, on the x-axis here, so that, let's call it P57 as usual, so that the probability that x is less than P57 is in fact 0.57. So this area here is 0.57. Well, we don't know the mean and standard deviation, so we can't do this by using inf-norm, which would be the natural thing to do since we know the area and we want the cutoff for it. So what we'll do is we'll transform over to the standard normal, right? And whatever this number is here, P57, it's got to come over to a number right here on the z-axis so that the area to the left of that number is 0.57. Now that means that this is just P57 over here. So we can get over here, though, we do know the mean and standard deviation. P57 then is just going to be inf norm of 0.57, comma 0, comma 1, if you like. And so let's see what that is. Inf norm of 0.57. It's about 0.1764. All right. Number 24. It is known that the time it takes to do an oil change on a vehicle has a normal distribution with mean 17.8 minutes and standard deviation 5.2 minutes. An auto service shop will give a free oil change to any customer who must wait beyond the guaranteed time to complete the work. If the shop does not want to give more than 1% of its customers a free oil change, how long should the guarantee be to the nearest minute? Okay, so here's the situation. We're going to let x be the oil change time. And then we've been told that x is normally distributed, right? This is normal with mean 17.8 and standard deviation 5.2. And what we want x is time here. We want to know where on this x-axis, where on this time axis to mark off so that the probability that an oil change takes longer than that is 0.01. So what this is P99, the 99th percentile. Okay? So here we do know the mean and standard deviation, of course, so we can just find P99. It should be inf norm of 0.99, 17.8, 5.2, and that works out to be approximately, let's see, 0.99, comma, 17.8, oops, not 52, that won't work well at all, 5.2, it's just about 30 minutes, rounded to the nearest minute. So they want to set that guaranteed time to 30 minutes, and that way no more than 1% of customers will take longer than 30 minutes. All right, that's it for practice test 2. Hope it helped.